Hello everybody, I Pulok Samanto of Department of Mathematics, Ramakrishna Mission Residential College, Autonomous Narendrapur, welcome you all in the second webinar organized by our department in collaboration with Department of Mathematics, Ramakrishna Mission Vidyamandira, Belur. Our today's topic is an introduction to Calderon's inverse problem by eminent speaker Anupam Choudhury of NISER, Bhubaneswar. Hope you will enjoy the talk. Now I want to invite Swami Sastraganandaji Maharaj, principal of our college, Ramakrishna Mission Residential College, Narendrapur, to give his welcome address. Maharaj.
Namaskar. Namaskar. Thanks to all. On behalf of the Department of Mathematics, Ramakrishna Mission Residential College, Narendrapur, I welcome you all in this webinar organized by the Department of Mathematics of this Autonomous College in collaboration with another reputed college of our Ramakrishna Mission situated at Belur Mott named Ramakrishna Mission Vidyamandira. In fact, both these two colleges have their reputation, have in their credit very high fame in teaching mathematics. Recently, our Vidyamandira College, the Department of Mathematics of Vidyamandira College has been doing well also in their research work, I know. They are also teaching postgraduate programs for a long time, more than 14 years they are teaching postgraduate program, offering postgraduate program in mathematics. And our Narendrapur College is also very reputed for the mathematics teaching, undergraduate mathematics teaching. What I have told at the previous day webinar also, I want to reiterate the same thing, that when two reputed departments come close together and collaborate in their academic activity, naturally academic peers get enriched. Academic arena become more luminous. Furthermore, today we have got amongst us Dr. Anupam Choudhury from NISER, who is very well known, is highly reputed faculty member, researcher of the institute. Although I am not a person of the subject, so naturally I will not be elaborate his expertise. But as I have come to know from the faculty of the Department of Mathematics of our college, they have told me once and again that although he is young, despite his youth, he has earned high reputation in teaching mathematics, in researching on mathematics. You see, knowledge is something which is always pure. Knowledge is something which is always expanding. Knowledge is something which always welcomes the inquisitive minds of the humankind. It is knowledge which has made this universe, made this human world civilized, cultured. It is this knowledge which will be able to usher in new lives in the horizon of, at the backdrop of this pandemic crisis. However, I, from the very core of my heart, on behalf of the Department of Mathematics, on behalf of our residential college, welcome Dr. Choudhury, and I expect that his deliberation, along with or followed by the introduction, will surely give new lives in the minds of inquisitive learners, students, faculty members, researchers, whoever listening today. I think at the program's end, they'll be able to switch off their screen with an enriched mind, and that will be the success. There will lie the success of this webinar. Once again, I welcome Dr. Pal Choudhury and welcome all the viewers and welcome our collaborating institutes, its principal Swamiji, head of the department, Professor Pal, and other faculty members, and also my faculty members in this discussion, in this webinar. Thank you very much.
Thank you very much.
Thank you, Maharaj. Now I want to call on Dr. Nonigopal Mandal, head of the department of our college, rather of our department, to introduce the speaker. Nonida.
Good afternoon, everybody. Now, today's speaker is Anupam Choudhury. He is our ex-student of the department. He passed mathematics honors from our department, Ramakrishna Mission Residential College, Narendrapur, since in the year 2007. Then he did
ননিদার কিছু একটা সমস্যা।
Okay, so I know. So maybe I can start from here.
Now I want to formally invite Dr. Anupam Pal Choudhury of NISER Bhubaneswar to present his talk. Over to Anupam, sir.
Thank you very much. Thank you very much for this invitation to give this talk at my alma mater. I mean, it's a very special occasion for me. So, yeah, so let me just try to share the screen. So I hope this is visible to all of you. So what I really want to do today is give an introduction to inverse problems in general, and more specifically to Calderon's inverse problem. So the first thing I want to mention is that this is not really going to be a research talk. So essentially I won't be presenting any of my research or anything of that sort in this talk. So my aim is pretty simply to give you an introduction to the field, because it's an exciting field which uses a lot of very interesting mathematics from different areas of mathematics. So that's my aim, just to give you a flavor of the thing. So the first half of the talk, I'll just stick to very different kinds of inverse problems. So there won't be too much of mathematics. I just want to give a very like a very broad overview of the topics. And then in the second half of the talk, I want to concentrate on the specific problem which arises from something known as electrical impedance tomography, which I'll obviously explain to you as I proceed. And that was proposed by someone, a mathematician come engineer, I would say, known as Calderon. And so therefore the name Calderon's inverse problem. Okay, so see, in life, it is very important for us to have some role models, right? We all have some role models that we want to follow. So let's start with some very famous personalities who are interested in inverse problems, okay? So I guess most of you are well aware of all these personalities. So because we have grown up with them in some sense. So okay, and don't. I hope you understand that this is not a wrong slide. So all of them are detectives, and so I want to really tell you what is the link between a detective and an inverse problem. Okay, so let's try to understand what does a detective usually do. Okay, so we have all been reading crime stories and these things. We have been watching movies and all. So let's see, what does a detective usually do? So usually there is some crime committed somewhere, and then a detective, usually with his or her assistant, walks into the crime scene, right? So in movies, whenever we see them, there's some very interesting background music on that is going on, and then he makes a dramatic entry and things. So, and then what does he do? So he tries to gather clues. So he inspects the crime scene, speaks to the maybe the relatives of the victim, and just tries to gather as much of information as possible, tries to gather as many clues as possible. Okay, and then he or she virtually reconstructs or tries to trace back the action of crime, okay, using these clues or informations. Right? So, I mean, there are many ways this is obviously done, and we all know, we have seen so many stories, and we are, the main aim is this: he wants to catch the criminal, right? So he has to reconstruct the entire action of crime in some sense, and he just have these some clues and some informations to play around with. Okay, but now if you think about it, this entire process is actually quite unstable. Okay, what do I mean by a very unstable process? So just think about it. We are all we all know that how this works. So even the slightest error in judgment uh, can get an innocent person convicted, right? I mean, if the detective or the police force, when they come, and if they make some error in judgment, judging the misreads their clues or doesn't get enough information or something like that, it is a very common phenomena that many innocent persons are also convicted. So that's what I mean when I say the process is unstable. So the error margin that the detectives or the police force they work with is very, very little. I mean, they don't have the liberty to make errors. So it's a very tough job, obviously. Okay, so and what is the link with inverse problems? Essentially, that's what I want to show, that inverse problems also involve the similar steps. Okay, so there will be a crime scene. Okay, in terms of mathematics, there will be some clues and informations, and then one has to reconstruct and then try to find out the criminal. Okay, all these things obviously we need to understand mathematically what this means. And again, we will see that the process is an unstable process. So there, if you make a very small error, there it gets magnified. Okay, so let's try to understand a very generic inverse problem. Okay, a very generic example of an inverse problem. So just consider an input theta. Okay, some input, there's some input theta here, and then suppose that this is transformed. This input theta is transformed into an output. Let's call it as k theta. Okay, so this k is the action. Okay, so it transforms theta to k theta. So then this k is called the forward operator. Okay, and the forward problem, when you say a forward problem, what do we mean? We mean that given a theta, we want to determine what this k theta is. So given an input, we want to understand what the output is. That is the forward problem. The inverse problem is the recovery of theta given the output k theta. Okay, so k theta, the output or some information related to the output is known to you, and you want to find out what this theta is. Okay, you want to recover the input that caused this output. So if we go back to the detective analogy, what is happening? K theta are the clues, okay, that the detective or the police comes in and gathers. Theta is the criminal, okay. So and this K is the action of crime. So essentially, using these clues, this k theta, one tries to find out who the criminal theta is, and also tries to somehow understand. And this would involve obviously trying to understand what the action of crime is, or k is. Okay, so you see there is a very simple analogy to the job of a detective and studying inverse problems. Okay. Okay, so let's now get to a little bit more mathematical thing. So we all know from our class 11th standard, so we know that the operations differentiation and integration. Okay, so what is the differentiation? You take a function f, and this map it just takes you to derivative. Okay, similarly you can take a function f which is integrable in some sense. So then f going to integral of f, that also gives you an operation, so another map. Okay, so now a question for you is, which among the two can be considered as an inverse problem? So you remember, whenever we have an inverse problem, we also have a forward problem. So the question to you is, which can we consider as a forward problem, and which one should we consider as the inverse problem? Okay, so the hint that I want to give to you at this stage is, small errors matter in case of inverse problems. Okay, and as you keep thinking, let's proceed. I'll come back to this afterwards, but please keep thinking. So which one should we consider as the inverse problem? The notion of differentiation or the notion of integration? Okay. So now, generically, there is no fixed set of problems that are called inverse problem. There's no fixed definition of this. So, but usually when we say that something is an inverse problem in mathematics, usually the idea is, that suppose there will be some object or something like that, and you want to understand that object, some properties of that object. So you send a probe. By probe, what I mean is something like, say, an X-ray, some pressure waves, some electromagnetic waves, acoustic waves, some electric current, etc. Okay, so and you send this waves or this probe towards or inside this object. Okay, so by object it can be just a medium also. So you are just sending these waves inside this medium, and then what you do is you measure the probe. So you measure the waves before, obviously because you are sending it, you know the waves or this probe before the interaction. But what is more important is also you can now collect the information or measure the probe after the interaction with the medium. Okay, and then what you do is you repeat this several times in several directions to collect enough data. Fine, and then what you do is reconstruct the shape or structure of the object using this information that you have collected. Okay, so in mathematical terms, this would involve recovering certain coefficients of a partial differential equation, or solving integral equations. Okay, so this is generally the field of inverse problems. So this is also obviously our focus will be on the mathematics part, but even there is an engineering aspect to it, because it is not suppose you want to reconstruct something. Obviously, there is a mathematics behind that, but also there is a engineering aspect to it, how to really reconstruct it in real life. Okay, so you see, this is a field where computational mathematics, theoretical mathematics, and engineering ideas, play. There's a very rich interplay between all these things. Okay, but again, so our focus will obviously be in understanding the mathematical aspects of this. Okay, so let me just give you some examples from what is known as this imaging problems, which arise in this class of inverse problems. So let me start with this very interesting example of an X-ray image. Okay, so this is the image of Annabert Roentgen. I guess most of us already have heard about Roentgen. So Wilhelm Roentgen was the person who in 1895 accidentally discovered X-rays. Okay, so he was testing. He was doing some experiments to test whether cathode rays could pass through glass or not. But then suddenly he discovered this a strange ray, some strange images coming up. So an unknown ray was playing some role. That is what he understood, but he didn't know obviously what ray was that, and but he surely understood that it is not the usual known rays that that was already known at that time. So therefore, he named it as X-ray. Okay, X stands for an unknown, right? So that is an idea. So so obviously once he discovered that, he wanted to, I guess, play around with this idea and get some images. So this is a very nice image. This is an X-ray image of his wife's hand. So I guess if I understand correctly, this is a ring, a ring on one of her fingers. Okay. And if you look at such a bit in Google or internet, I mean, you'll see that Anna Barthe played a very important role in the scientific career of Wilhelm Röntgen. So, yeah. Okay. Next few examples are, coming from medical imaging and all. I understand this is not the right time to show all these, bad images. You all want to avoid these things, but okay, it is very important from the perspective of imaging and from our daily life. So this is just a slice of a CT scan, okay, of someone called Michael Hagstrom. Okay, obviously I do not know how to read these things, but I just want to tell you that again, all these things are from Wikipedia and things. So there is some. He was having some brain tumor or something like that. So essentially, that sort of a issue was found out through this CT scan. But what I want to notice is, if you have not already seen CT scans earlier, see just the clarity of the images. I mean, so how beautiful this is, so you can really capture what is the happening inside your brain, inside the tissues and the structure. What if there's something wrong? If there's some tumor going on, and just look at the precision of the images. Okay, so this is all achieved through this imaging modalities. Okay, and these are all parts of these inverse problems. Okay, so and this is obviously many of us have already faced this in life. Some of us will probably have to face this in life. This is known as this computerized tomography thing. So essentially, it takes so the CT scan. So essentially, this is where a patient lies, and then suppose a scan of the head is to be taken. So the head is placed here, and you see this black portion here. That is essentially the place where rays are emitted. Okay, so usually X-rays are used. So X-rays are emitted, and then the image is taken, and then obviously the doctor reads it and then tells us about the issue. Okay, so let's. So how is that done? So you remember when I tried to explain what exactly we usually mean when we're talking about inverse problems, that we need to collect data as much as possible. Okay, we have to repeat maybe the process several times to understand and collect more and more data. And that is what exactly happens in X-ray. Okay, these images are a bit vague, but if you look at this, so this is the patient here. Okay, and so from here, this is the emitter, and these are the X-ray detectors. Okay, so you see, first starting from here, some ray is emitted, and then it is detected here. So that gives you some image. And then what one does is, it is placed at different. So this emitter is placed at different areas here, and the image is taken. Okay, so this, you see from here, and then here is moved here, and again the same thing is done. So rays are emitted and detected using this. So, and this at least a few times this is repeated, so that you can collect enough data through enough angles, so that you can then infer something properly from using these CT scans. So the other type of problem that you see is, again, all this, if you think about it, these are very physical examples because we have already encountered such things in our daily lives. Okay, so we already know scattering by obstacles, right? So suppose there is an object, okay, some obstacle, and you keep sending some waves, okay, So obviously, at some point it will go and hit this one. And what happens after that is, it gets reflected. Okay? So essentially you can think about this as this original waves as some incident waves. And then there are these reflected waves. Okay, so at any point, if you see, so these red ones are the incident waves, and the green ones are the reflected waves. So at any point, if you look at it, the waves are a mixture of this incident waves and this reflected or the scattered waves. Okay, so but you already know what the incident wave is. So whenever the entire idea of this mathematical theory of scattering, especially by obstacles and all, is to understand this the properties of the scattered wave. Okay, so and that essentially using that you can detect maybe the shape of the object, the position of the object, and various very interesting properties, okay, of the medium. Okay, and so this obviously these pictures here the sender and receiver is at the same position, but that is not necessary. You can have a sender here and then a receiver here or at some different point. Okay, the sender and receiver need not be the same one or need not be positioned at the same point. Okay, so this is another very important aspect. So this is known as the mathematical theory of scattering by obstacles. Okay, it's a very, very important theory, and integral equations play a very important role in studying these things. Okay, so even in optics, when we study optics, if you remember, we encounter something called plane waves. Okay, so these plane waves are something that comes up when you study this scattering by obstacles, okay? The mathematical theory of that. Okay, again, another example that is here that I want to give you is of this intravascular imaging. Okay, so what is this? So usually, suppose you want to detect some plaque, okay, or some sort of sedimentation, whether in a blood vessel. So what one does is one puts something like a catheter inside your blood vessel, and this catheter would have some sort of a emitter. So some what is called here the transducer sometimes. So it's essentially it will emit some beam. If you look at this, it will emit some beam. Okay, and then depending upon the reflection, so again there is some scattering, because you see obviously the properties here. So if you just think about it, suppose I am sending some sort of a wave. So the time that it will take to reach here to here will surely be much more than the time it will reach from here to here, right? Because, and obviously we have some understanding of the time that is usually taken to reach a healthy tissue. So therefore, since we know that this is something like lesser time is taken, probably these are the locations where there is some sort of a sedimentation or some plaque, okay, in the blood vessels. So that is the somewhat a rough idea that goes inside this intravascular imaging. This is obviously, we have seen this so many times in our life from our early childhood. So we want to understand the seabed, right? So what we do is we put some sonar waves and all, and then it goes there. Some guns sometimes, the early, there's some guns were used, and then these gunshots were used, and then this sound obviously goes there and gets reflected back, and using the time that is taken, one can then understand what is the image of this seabed or the riverbed. Okay, so you see this is a three-dimensional image reconstruction problem, imaging techniques. So you see there are many such examples you keep seeing in real life where we actually use an inverse problems. Why are the inverse problems? Because we are collecting some informations like this, and then because we do not know exactly what is this. Okay, we are collecting informations and trying to infer or reconstruct how the things look like. Okay, so that's why it's some sort of inverse problem. Again, the next example that I wanted to discuss with you is about this radon inversion. Okay, and this X-ray tomography. How does it work? So essentially, what is this? So you have this unknown parameter mu usually, which this mu is. So you have this object, okay, that is to be imaged. So this mu is some unknown parameter which models this object. So mathematically speaking, sometimes, okay, let's just keep it simple. So this mu is some parameter that if we know, we can infer a lot of properties of this object. Okay, so this is also called the attenuation coefficient of the object. Okay, so then if you use Beer's law, so this is essentially Beer's law, so which gives you a relation between the intensity of these waves and the intensity of the X-ray waves, and then with the position x, okay, and the position x. So, and using this, so now obviously we know. So what can we do if you look at just this one? See, we know this is some infinitesimal quantity. So usually whenever we say this, we immediately formally what we do is, okay, delta should be replaced by d. So delta I is di, delta x is dx. Pretty good. Let's integrate. So if we integrate it, what do we get? So see, now if we integrate along these lines, okay, along these lines L. So suppose I have, so this is my transmitter. So this is giving you the X-ray. So it is passing here and penetrating the object or going through the object and then going here. And this is the receiver. So these are moving in straight lines. So then if you look at this, I know the intensity at this level of the X-ray because I am the one who is sending it. Okay, so I know what is the initial intensity. I can read the final intensity from the receiver. Okay, so I know the final and the initial intensity. So then that means if I can integrate over these lines, I can probably say something. So essentially I can integrate over these lines, and then the integration will give you, this is the natural logarithm of I final by I initial, just plain integration. We know I final and we know I initial. So obviously we know the logarithm of the quotient of them. So what do we get? So this idea of Radon's X-ray transform or this X-ray tomography is that we know we wanted to understand this unknown parameter mu, or the informations that we have are essentially the integration of this function mu over these lines. So the question is, from this information about the integration over lines, this information we know because we know that this is exactly this one, and we know I initial and I final, which can be measured. So essentially, if we know this integral over sufficient number of lines, can we say something about mu? Okay, can we find out mu, say, in a very simple way, whether that is possible? So this is a very simple mathematical problem that was studied by Radon. Okay, and from an absolute mathematical perspective. So he had, I don't think he even considered about X-ray tomography or anything. It was a very simple mathematical problem. Given a function mu, I know its integral over lines. Can I recover this function f, sorry, function mu? Okay, so that's a very simple mathematical problem, and that is though it looks and sounds very simple, that is one of the very cornerstones of this integral geometry, subject of integral geometry, and which is usually studied as a part of harmonic analysis. So this is a classical inverse problem. Afterwards, obviously, this idea of Radon, a very mathematical idea of Radon, was taken up by Cormack and Hounsfield, and they applied to this computerized tomography and medical imaging, the practical applications of this idea, and therefore they got the Nobel Prize in 1979. Okay, so you see, it was a very simple mathematical problem. Again, when I mean simple, it sounds simple. It is not, the solution is not simple. So it simply, it was studied from a very mathematical perspective, and then afterwards it was applied, and it is one of the most important things in our daily life nowadays, X-rays, CT scans, and all those things. Okay, I'll just go back to the other images. So you see, okay, this X-ray transform, what does it do? It tries to recover the function, say f or mu, whatever the function is, from its integral over lines. Okay, so this is obviously a 2D problem. In higher dimensions also you have the same problem, same question you can ask, and that would be like you have the integral, you know the integral of the function over hyperplanes, and can you, from that information now, can you recover this function, or you can, whether you can say something about this function, okay? And this is over hyperplanes and lines, and if you look at actually this all these imaging things, this one and even this problems here and all, so they give rise to other very important notions as circular radon transforms, elliptic radon transforms. There are very, there are variants of this very early, this usual line transforms. Okay, so and this called elliptic, circular, spherical. There are many such variants, and this is a very interesting topic of research. It is which is also comes under the integral geometry. And this is a part, obviously, this is a classical inverse problem. Okay. Okay, so now let me get back to slowly get back to the very important idea of as I said when I asked you about this question about differentiation and integration, I guess some of you already would have guessed the right answer. So the idea is small errors matter. So let's get back to the course of differential equation that you usually have in the university. Okay, so if you look back to the syllabus that you studied there, one of the most fundamental result that is taught is about the existence and uniqueness of a solution to an ODE or a PD. Let's just stick to ODE. Okay, given a ODE, can you find a solution, existence result, and whether the this is unique or not? Obviously, a lot of time is spent of some ad hoc techniques to solve those problems explicitly, but usually, obviously, that is not possible. So, I mean, in general ODEs, rather most ODEs you won't be able to solve explicitly in terms of some formulas and all. But then there are some theories which tells you about the Picard's existence theorem and etc., which tells you about the existence of a solution, a certain condition, also whether the solution is unique. If you notice very carefully, there's another theorem, a result which is usually kept there, that is about stability of the solution with respect to the various parameters present. Okay, for example, if the initial data are close enough, you obviously expect that the solution, okay, even if it is unique, this is also the corresponding solutions of the problem, if you choose very close initial data, should also be close. I mean, it should not use, it doesn't make much sense if you really start very close and suddenly you find yourself going bonkers. I mean, you don't know where you land. Because if such a thing happened, so if the stability is absent, then numerically, if you want to study these differential equations, that's a huge issue. Because you usually in numerics, we will always have some kind of errors, right? Whether the error in measurements or error in the the computer has some its own inherent round of errors and all those things. So therefore, you will always make errors. So you always want to make sure that the problem that you study is stable. So if you even make a small bit of error, the corresponding solutions that you get are also nearby. It's not really very far away or different. Okay. So usually the forward problems that we tackle in mathematics are well posed. Okay, so it has existence, it has uniqueness, it has the good property of stability. But inverse problems are generally ill-posed. Okay? And ill-posed means the stability is absent. So even very small error in data can get magnified in the case of inverse problems. So you see, again, coming back to the detective thing, the job of a detective is indeed a very difficult one. It's an inverse problem. Usually it's ill-posed, so they cannot really make, they're not even allowed to make small errors as such. So now let me go back to the example concerning integration and differentiation. So differentiation is an ill-posed operation. Okay, this is something you can very easily one can find out some examples using the norms. You can show that this is, even if you change the functions a little bit, differentiation can make it wrong. There won't be any stability. Okay, so differentiation is something you can consider as the inverse problem corresponding to the more stable problem of integration, which you can call it as a forward problem. Okay, so that is also the answer to the question that I asked you at that point. Okay, so now, so essentially this is the first part of the talk, and let me try to move on to the second part, which is about electrical impedance tomography and Calderon's problem. So this is going to be slightly mathematical again, but this is a very interesting, some very interesting mathematical ideas go inside this one. Okay. So let's see, this electrical impedance tomography, you see this usually many times when you want to image the abdomen, say, and all. So you have this something EIT device. What they do is you give this current injections. So injection, don't think about those sort of injections. Like you pass some current through this, okay, and then you measure the voltage and things like that. So you have this electrode belt which sends some current inside your abdomen, okay, and you see this, and then you see the response that comes out. Okay, and also in studying, when the doctors study this mammography, so in the study of breast cancer. Okay, so this is a usual technique that is used, this EIT. Okay, so now motivated, by the potential application of this electrical impedance tomography. Obviously, he didn't. Calderon was not really motivated from these medical examples. He was more interested in oil exploration and wanted to see whether this idea of this electric prospection, whether this type of an idea using this electric currents and this current and voltage measurements, whether using this one can understand this oil exploration thing. So the idea is that by making steady state voltage and current measurements at the boundary of a medium, can one recover the conductivity of that medium? Okay, so this is the question Calderon asked. So in a very mathematical terms, essentially this means that you are studying a partial differential equation of this form. Okay, so this grad dot, this is the conductivity gamma. Okay, and you have this boundary measurement given, boundary data given as F. Okay, and so if you assume this gives you some sort of an ellipticity condition, and that allows you to infer the well-posedness of this problem, the forward problem. Okay, so given this F, you have to find out some U. Okay, and you know gamma, you know F, you want to find out the solution of the problem. So the forward problem, so that is what you want to find out, U. So this is possible usually under these conditions. Okay, so now once we know that the well-posedness is there for the forward problem, okay, what about the inverse problem? So inverse problem would be to understand this conductivity of the medium gamma. Okay, what do we know now? So idea is, think about the earlier example. So this is the current that you are sending, say, okay, this F, and then these are the boundary measurements. Okay, so the boundary measurements will come up. Now you can solve this equation. Okay, so you at the boundary is F, and then this gives you a unique solution, and then you can have the Neumann derivative, gamma times Neumann derivative, look at that quantity on the boundary. So this is kind of this current here. Okay, so the question is whether you can uniquely recover the conductivity gamma. So this N gamma is known as the Dirichlet to Neumann map, okay, and also known as the voltage to current map. So now we are interested in the inversion of this map. Okay, so whether if we know N gamma, can we get gamma from this one? Okay, so now this is a non-linear problem. Okay, so essentially it's so therefore it becomes pretty difficult. And so in his fundamental paper, so the first paper that Calderon wrote is a very interesting paper actually. Some very interesting ideas have been used there. So Calderon, but he was not able to tackle the inversion of this non-linear problem. Okay, so what he did was, and that is pretty usual technique in differential equations, if you are not being able to solve the non-linear problem, you at least try to linearize the problem and try to at least study the linearized problem. Okay, and whether you can do. So he also took the same strategy. He linearized the problem and studied the corresponding linear map near constant conductivities. Okay, so in that case, the linearized map, is like given by this Fisher derivative of the following map. Okay, so this Q gamma going to Q gamma, where this Q gamma is defined in this form. So Q gamma of F is integral of omega gamma times grad U square. Okay, and where U satisfies this is a solution to this equation. Okay, now if you just integrate by parts, you can very easily see that this one is exactly related to the Neumann map. So this is related to this map. You see this and this, okay? So they are equivalent formulations, whether you study the Neumann map or this Q gamma for the linearized problem at least. So what does it do? So then, this linearized map, so you get this integral. So the above integral, you see, one can say that it vanishes for all u satisfying, delta u equal to 0. U, the boundary is f. So if and only if you have this un and u2, so for un and u2, which are solutions to grad this Laplace u1 and Laplace u2 equal to 0, if this is satisfied. Okay, so it just needs a little bit of calculation, but it's quite easily done. Okay, so the question now is, so the entire question that you can ask, transform into this particular question is, if this quantity is 0 with where u1 and u2 satisfies this, can you say that delta is 0? If that is done, then we are done. Okay, so then you can immediately say that we can recover this one for the linearized problem at least. So again, look at this. Idea is, question is, if this is 0, can I say that delta is 0? So Calderon, he proved that the answer is yes, obviously. So very simple, but the technique is extremely powerful, because what he did was he looked for special solutions, okay, to this problem, Laplace equal to 0 of the form uf equal to e ix dot zeta, where zeta is a complex number. So again, at this point, I would like to bring to your attention the these plane waves. You remember the plane waves that we study using in optics courses and all. Okay, so these are these plane waves and all these things. They are like very special solutions, and not only they're special, and they're very powerful solutions also. Okay, you can do a lot of things with them. So as you can see, this is a very close relative to the this plane waves. Obviously, the difference is that now zeta is a complex number. So now, if this u has to satisfy this equation, then you have to put a condition like zeta dot zeta equal to 0. Okay. So using this sort of solutions, what he now did was he fixed some. Okay. So the idea is to from this integral, somehow transform it into an information about the Fourier transform of delta. Okay. So suppose by some way, if you can prove that the Fourier transform of delta is 0, then immediately you know that okay, then delta is 0. So that is the idea. So using the special form of solutions, so what it is, so when you want to understand the Fourier transform of something, and you want to understand it at some frequency z, right? So this is that z, that frequency where you want to understand the Fourier transform. So using this z, you can construct this zeta 1 and zeta 2 of this particular form, which satisfies these conditions. Now you just take your u1 and u2 of this form, so e to the power ix dot zeta and zeta 1 and e to the power ix dot zeta 2. If you use this sort of special solutions and plug it here, obviously they satisfy this. Immediately you see that what you get from this relation is that the Fourier transform of delta is 0. Okay, so you essentially get something like this. Okay, so mod zeta square by 2 is 0. So obviously, except for 0, this is this part is not going to vanish. So delta had z is 0 almost everywhere. So except that one particular point, and this implies immediately that delta equal to 0 almost everywhere. Okay, this. So if you know measure theory, you will know that when I say almost everywhere means it is except for some funky points, everything is fine. Okay, so you see, the main idea is in this entire idea of the Calderon was to simply use these special solutions. Okay. Obviously, he couldn't deal with the nonlinear problem. So a few years after that, the invertibility of the nonlinear problem was shown by Sylvester and Ullmann. It's a wonderful paper, and I'll try to explain to you the ideas. Obviously, the ideas were like extension of the ideas of Calderon. So they introduced a very powerful and very versatile technique for looking for special solutions, okay, to this lower order perturbations of Laplacians. And this type of solutions are what are called complex geometric optic solutions. Okay, so what did they do? So first of all, they noted that the conductivity equation can be transformed into a Schrodinger equation of this form, okay? So using this sort of a transformation, so idea is if you can now recover Q from this, okay, if you can recover Q, then you can also recover this gamma, okay. So essentially, you just need to study the Schrodinger equation instead of this. Now, what is interesting about this Schrodinger equation? If you look at this, sorry, Q is a lower order perturbation of the Laplacian, okay. So Laplacian is a second order differential operator, right? So Q now here is like a 0th order operator. So essentially it's a lower order perturbation. You can just think about, you have the Laplacian, a second order operator, you perturb it, okay, by something of a lower order. So that is the Q. Okay, so now the question that you want to understand is, obviously we can similarly, as in the case of conductivity equation, we can have this Dirichlet to Neumann map corresponding to this one. Can we determine Q? Okay, so what was the idea that Silverstein Ullmann used? The Silverstein Ullmann used a very nice trick. So the idea was, okay, we know Laplacian of V. Okay, we know those spatial solutions that Calderon considered. Now we are considering an equation which is a perturbation of those Laplacians. Okay, why not try with the perturbation of those spatial solutions? Okay. So what for them the answers was this. So you see, this is the e to the power I x dot zeta that was given by Calderon, introduced by Calderon to study such problems. And then, okay, just for time being, take a equal to 1. Okay, you see, this is the lower order perturbation, okay, of this the special solution that was given by Calderon. So my problem, the Schrodinger equation, is a perturbation of the Laplacian, okay, lower order perturbation. So my answers, or the answer that I want to find out, I can always think about it as a perturbation of the special solutions that I have already for the Laplace equation. Okay, so that is a very simple idea. Obviously, now you have to work a bit to understand when such a this remainder term, the R, this perturbation exists. Okay, so then you can see that the R is something of is also called a correction term or a remainder term. So this R has to satisfy this sort of a equation. Okay, so if you can solve this sort of equation and get some estimate, good estimate over R and this derivative, then you are done. Okay, so that is now, that is the beauty of that work, obviously, of Silverstein Ullmann. So they proved the existence of this R and also showed that R satisfies some estimate of this form. Okay, so the L2 norm of R is like decays in terms of this zeta, mod zeta, and the gradient, the L2 norm of the gradient of R is bounded. Okay, and this Vx, these are solutions which are known as the CGO solutions. Okay, now what they will do? Okay, so again, they just use the integration by parts. So if you use this Green's identity and use that from here, you can immediately derive an identity of this form. Okay, so integration over Q V1 V2, where V1 and V2 are solutions to the equation, the Schrodinger equation, but now with potentials Q1 and Q2. Okay, and this Q is just the short form, the difference between Q1 and minus Q2. So essentially, you have integral of Q1 minus Q2, V1 V2 equals to 0. Okay, just go back, and think about what Calderon had there. Calderon had something like an integral of delta and some gradient of some U1, gradient of an U2. What was the idea there? The idea was, can I recover or show that the Fourier transform of that delta is 0? Idea here also is the same. Can we somehow recover some information about the Fourier transform of Q? If I can show the Fourier transform of Q is 0, then I'm done. Okay, so obviously again now the idea is to find solutions V1 and V2 that are close to the e to the power I x dot zeta. Why e to the power I x dot zeta? Because if I have e to the power I x dot zeta here, that will give me the Fourier transform of Q. So I have information about Fourier transform of Q. Okay, so if you consider the dimensions n greater than or equal to 3, the proof is slightly easier. So what you do is you fix some zeta, the frequency, and then choose some orthogonal vectors, okay? The C omega 1, omega 2. Because you are in dimensions n greater than equal to 3, you will always have at least 3 such orthogonal vectors, right? And this is very important, and this is also the reason why this particular technique doesn't work in 2 dimensions. Because here we need to choose this set of 3 mutual orthogonal vectors. Okay, now once you have chosen that, you define your zeta to be of this form. So S omega 1 plus I omega 2. And you define your special CGO solutions in this manner. So V1 and V2 are look like V1 e to the power ix dot zeta times that A that was there now is 1 plus R1. This is the correction term. And similarly, you have this V2. So you have this e to the power ix dot zeta, and you have this e to the power, now the A is e to the power ix dot z plus this this one. So again, that A there, that point I skipped it. So you see that it just needs to satisfy this equation. So any A that satisfies this is a transport equation, satisfies this is allowed. So one can show that e to the power ix dot zeta will also satisfy this. So therefore, I can also take this one there. Now, due to the decay, so remember that there was some decay estimate for R1 and R2 with terms of this zeta, this parameter zeta. Okay, this zeta. Because of this, we can prove that the Fourier transform of Q is 0. So you plug everything here and see that one of the main term, the leading term, will give you the Fourier transform of Q. The other terms will go to 0 as mod zeta tends to infinity. Okay, and how do you tend mod zeta to be infinity? Look at this parameter S sitting here. Okay, so this parameter S, you can take it as large as possible. This will give you a class of such zetas that you can play around with. Okay, and that is what you use here. And so as soon as you have this information, you have the proof that Fourier transform is 0. Hence, Q is, you can immediately conclude that Q equal to 0 almost everywhere in Rn. So the theorem is valid in 2 dimensions as well, but the proof is different. Okay, so this technique doesn't work in 2 dimensions. And in dimension 1, you can very easily see, if you just write down the equation and integration and do an integration maps, that and in general you cannot expect an uniqueness result. So in general you cannot expect to recover the conductivity. Okay, so in dimension 1 is doesn't work in general. Okay, next comes to the question of stability. So I guess I would have to take around 5-10 more minutes. So question of stability. Remember that we obviously want to understand whether if we make a small error, whether the error gets magnified or not. So the question of stability is this. So if gamma 1 and gamma 2 are 2 conductivities, okay, such that those maps, the measurements, okay, remember that these are the clues, okay, that you have, the measurements or the data that you get, the information that you get. Okay, this gamma lambda 1, gamma lambda 2. And you want to, from these clues, you want to understand about gamma 1. Okay, you want to recover gamma 1, you want to reconstruct gamma 1 and things like that. Okay, so now suppose these 2 are close, can I say gamma 1 is close to gamma 2 or not? So more precisely, we are looking at an estimate of the form. So can I control the L infinity norm in terms of, don't bother too much about what is a Sobolev spaces where you make these measurements. Doesn't matter, it's some distance on the space of the measurements. Okay, so question is whether we can control the L infinity norm of the difference between them in terms of this the distance or the norm of the difference between the measurements. Fine. So in general, if you have Lipschitz stability, what does Lipschitz stability means? Lipschitz stability is the one which is proposed by Hadamard. So essentially, you make small errors, your solutions are still small. Okay. So if omega t, that is something called as a modulus of continuity. If you take omega t equal to t, okay, that means omega of this one is just, you'll have this term. You can forget the omega. What would that would mean that if this is small, this is also small. Okay. So question is whether we can have that sort of a Lipschitz stability estimate or not. Answer is no. And there was a very wonderful counter example given by Alessandrini. Okay. So Alessandrini considered this particular example and considered 2 conductivities, gamma 1 and gamma 2. The first conductivity with gamma 1 was uniformly 1. Okay, in the domain. So here the domain he took was the unit disk in R2. And gamma 2 he just modified a little bit around 0. Okay, so he just modified gamma 1 a little bit around 0. Okay, so one can show that you see this if you look at the L infinity difference, what is the difference between this? This is just given by A. Okay, but what about the smallness of this? So if you look at the measurements, if you measure them, you see that that depends upon this constant A, the modification that you made, and also the region, okay, the radius, where you actually, radius of that region where you made that small. So if you expect something of a stability result of this form, then what do you expect? When this goes to 0, this should go to 0. Look at this, what is happening here. Though this is going to 0, as R0 goes to 0, gamma 1 minus gamma 2, the L infinity norm of gamma 1 minus gamma 2 doesn't see R0 at all. Okay, so it is always A. It doesn't change with respect to R0. So therefore, even though the right hand side is, so therefore you see that this is not possible, because even though that this side is going to 0, this side is, a strict positive constant. It doesn't change. So therefore, you cannot have a Lipschitz stability estimate. So then, okay, what can we have? What we can have is something known as a logarithmic stability estimate, right? So let me not get into too much of the details. The idea is, again, for the Schrodinger equation, you have a estimate of Q1 minus Q2 in terms of this, but now it is not a Lipschitz stability estimate, but this is like a logarithmic estimate. So it is like a log of this term. Okay, so these are known as logarithmic stability estimate, and this also, this example also tells you that you should actually somehow be prepared for a result like this, because inverse problems are in general ill-posed, so you cannot expect Lipschitz stability usually. Okay, and so therefore you see that one has to work with a logarithmic stability estimate. See, this is a bad estimate, okay, because if you even make a small error, so suppose t is very small, okay, near 0. Okay, so mod of log t is very large. So this is not a very good idea. I mean, the good term. So the error gets magnified. But still you can quantify it somehow. That's very important thing. Okay. And similarly, you can transform all the equation from the Schrodinger equation to the conductivity one. And therefore you can again have an estimate of this form. So difference in L infinity norm of gamma 1 minus gamma 2 can control by a logarithmic stability estimate in terms of the difference between lambda gamma 1 and gamma 2. Okay, what are the other related problems that were studied? This, after the work of Sylvester Ullman, there are thousands of papers, I guess, already on different kind of inverse problems and using these techniques and all. So there are one very important thing is, here we were just taking 0th order perturbation of the Laplacian. Okay, what if we perturb it with a first order perturbation? Okay, plus a 0th order. So now magnetic Schrodinger equation. Okay, so you have a first order potential W and the 0th order potential Q. So you can similarly define the Dirichlet to Neumann map. So can one determine the potential Q and the magnetic field W from this measurements in WQ? Again, this was studied, this is now more or less well studied. Obviously, there are many aspects which are still open, but okay, we don't get into all those things. So, but thing is, W cannot be determined usually. There's something called a gauge invariance. Okay, so because of that, you can only determine certain components of W from boundary measurements. Okay, remember when W is 0, so when W is not present, we just saw that Q or lambda 1, or this gamma, so Q or gamma can be recovered in dimensions n greater than equal to 3. Okay, fully. But here, W cannot be fully recovered. You can only have a recovered component of W, but you can still recover the potential Q. Okay, the 0th order perturbation can still be done. Okay, so this is another very important related problem. So there are other related problems. Obviously, if you go back to this, this is a kind of full data problem. Why is this a full data problem that we studied? Because all these measurements that we made here, this del U, del nu and all, let me just go back and show this to you a bit. Yeah, you see these measurements that we made it over the entire boundary of omega. Okay, but in general, you won't be able to measure it over the whole boundary. Just think about if you're trying to detect breast cancer. Okay, I mean, you cannot really go to the other side of it, right? Because you have the backside of a human body. So that is not going to work. So you have only partial data. You can take measurements only on one side, or some partial data measurements. So partial data problems becomes obviously, they are problems. They are much more complicated, and so obviously they are studied. A lot of problems are studied, and there are many ongoing works. So from a physics again, so the partial data problem is another class of problems that people are interested, obviously. So from a physical point of view, as I mentioned, the entire boundary may not always be accessible, and you have to be happy with only measurements only on a part of the boundary. And such cases were also studied by Bugyam and Ullmann, Koenig, Jost and Ullmann. And again, if in case the measurements are available on slightly more than half of the boundary, the same technique that we discussed now with the CGO solutions will still work. But in general, if you have the portion of the boundary becomes smaller or something like that, then you need a much more refined version of the CGO solutions. And that was some results in that direction were proved by Koenig, Jostrand, and Ullmann, and it uses some very important techniques from microlocal analysis, using limiting column and everything. Okay, so this is more or less the end of the topic. So what I wanted to really tell you in this talk is, obviously none of these are my research. These are very all the things that I presented to you are more or less around say 15 to 20 years old. But you see the main ideas are there. But there are those fundamental ideas that were used to study those problems. Okay, that is what I wanted to emphasize in this part of the talk. And I'd also like to thank Professor Krishnan from TF Bangalore Center, because some of the slides that I have used, some pictures and all, were from his slides, so he kindly allowed me to use them. So I also wanted to give you some references. So these are some introductory books that you can look at. This is a very interesting lecture note which tells you about the mathematics of Calderon problem. It's a very nice place to start with if you want to understand the Calderon problems. Okay. And so I just like to dedicate this to PB. Unfortunately, he left us too soon. Yeah, and thank you very much for the attention.
Thank you, Dr. Pal Choudhury, for nice presentation. Now I ask, there are two questions. Before that, I want to ask Dr. Nonigopal Mundal to say something about Dr. Pal Choudhury.
Due to some technical problem, I was disconnected. So I want to introduce our speaker, who was our student also. Actually, he passed from the Department of Mathematics, Ramakrishna Residential College, Narendrapur, in the year 2007. Then he did MSc in 2010 and PhD in 2015 from TIFR Center for Applicable Mathematics, Belur, through integrated PhD program. He has also 3 years postdoctoral experience from 2015 to 2018 in the University of Basel, Switzerland, and Technical University of Darmstadt, Germany. And after that, he joined IIT Indore in 2018 as an assistant professor of mathematics. At present, he is working at NISER, Bhubaneswar, and joined here in 2019. That's all.
Thank you, Nonida.
Thank you very much. Thank you.
Now, Dr. Pal Choudhury, one question from, actually there are 3 questions. One from Saptak Das. The GAN model can we calculate the time? He asked that.
The sonar thing, usually yes. I mean, that is what is usually done, right? So I mean, you calculate the time, how much it is taking in some sense. That is one of the usual ways. Yeah.
Another question from the same person. In Lipschitz stability, whether 0 less than omega less than 1?
I guess he's trying to ask me about the modulus of continuity there. So the modulus of continuity for Lipschitz stability, you have to take this omega t, that function omega, to be the function which takes t to t. So omega t equal to t. Okay. So that is
Soumodip Mondal asks, please discuss the problem you given in the beginning of the lecture. I don't know what is that.
Which problem exactly? I don't understand. See, I don't understand. Yeah. So, but I think there's another question by someone called Krishna Kumar Pandey. Is there any definition?
Actually deleted that question.
Actually, question was, is there any definition of forward movement or K, like Laplace or K transforms?
No, so here we have
and he
actually
deleted that.
Oh, okay. So essentially, it's a very the example that I use is a very generic example. So K can be anything. You can just think of K as a very simple map. Okay, it takes theta to something. So input theta goes to K theta. It can be just a very simple map. You can think about it. It need not be some fancy Fourier transform, Laplace transform, Z transform, or something. Anything else. It can be any generic map. Okay, that is simple. Yeah.
Another question is, what is the application of inverse problem on medical science?
Oh, I mean, that is what I was trying to illustrate in the first part. So essentially, all those imaging techniques that you saw, so they are actually essentially inverse problems. This X-ray, as I mentioned, I mean, the idea is that you have these integrals over these lines. Okay, so that is the information or the measurement or the clues that you have. And then the inverse problem obviously is to understand that function which gives you these measurements. Okay, so even if from something as simple as X-ray is an example of an inverse problem. Okay, so that is the example. There are numerous such applications. This sonar, radar imaging, and all those things. All these things, the CT scans and everything. Even EIT has this applications in mammography and all those things. When you're trying to image the abdomen and things like that. Yeah.
Another question just came. The same person, Soumodip Mondal. The problem you given in the beginning was, which is the inverse problem, integration or derivative? That was discussed, I think.
That was already discussed, that differentiation is a inverse problem. You can consider differentiation as an inverse problem and integration as a forward problem. Yeah.
Another comment from our departmental colleague, Dr. Parthasarathi Mukhopadhyay. Very nice and lucid presentation, Anupam. Feeling proud of you.
Thank you very much, sir. I'm really happy that you could find some time to listen to this talk. Thank you. Thank you very much.
Can you please share the slides?
Okay, I can obviously share the slides, but how do I do that is a question. So I can either send it to NM, maybe you can post it somewhere in the website or something, then one can probably see that. Yeah, so I can obviously, there's nothing, I can obviously share it, yeah.
Okay, then Nonida, okay, no more questions there. Now I want to invite Dr. Kartik Chandopal, Head of the Department of Mathematics of Ramakrishna Mission Vidyamandira, Belur, for giving a vote of thanks. Sir.
Well, good afternoon, everybody. Dr. Nonigopal Mondal for giving me the opportunity to put a finishing touch in this fine webinar. And then I thank to the principal Narendrapur, previously our principal, Shastoganandaji, for giving inspiration, encouragement, and cooperation with us. I love the students of both the Vidyamandira and Narendrapur Residential College. And then finally, I'll thank to our speaker, Dr. Anupam Pal Choudhury, for his valuable presentation in this webinar. Thank you all. Okay.
Thank you, sir. And
okay,
thank you, Dr. Pal Choudhury. I think all the participants had enjoyed the talk. Thank you all.
Thank you.
Okay, so I'm leaving the meeting then. Okay. Yeah.
Okay.